Okay, there we go. So this is where we had left off last time. So we're going through the same set of slides. Here's room for lots of questions and things. So we had talked about the end of this one was how do we actually get the hull, the outside, because we have to figure out the path. And it does two different types of behavior. Figuring out how to switch between them, you have to know the exact location or pretty close. And by pretty close, we really want it down to the voxel. So anyway, this is where we had left off. These were actual scans that showed us stuff. We're going to now talk about briefly how we use that to calculate those entry and exit points and then move on to the next steps. This is kind of fairly straightforward if you think about it. Since the air, and that includes the volume up to wherever the boundary is, we're going to take the 2 points it hits and we'll project it forward from the entry point, and we'll take 2 points and project back from the end. If you're using one of the beam scanning systems where you have a very accurate idea and you don't have the upbeam ones, then you're just going to usually assume it's coming in from 0 and then at, or angle 0 and then at whatever spot your scan is coming in on. Now, I want you to think a little bit about just the hull, and that's what I'm trying to show here. There's a blue and a black one overlapping each other. And then I grabbed points with about the same angle, and I just did a quick spline fit to it, just to kind of get an idea of if you have a larger one, you get a completely different path, right? Because it doesn't have to do as much of a change, right? So that allows you to take a slightly different trajectory. This is why the size of it is fairly important as a whole, because otherwise you're going to get, different voxels, particularly kind of more of the mid-region. This one, they overlap in the middle because there's actually an inflection point. Right? It's coming in and it's going out in this upper angle, so it's got to change twice to get there. It would only have to change once. There'd be no inflection points in there, and you would only have crossings at the end. Right? This is just a function of the way I kind of do those angles. If this line had been lower down, it could have just done it by a simpler, softer one as a transition. Anyway, that's kind of the basic flow of this one, right? Again, we need that point, air projection, and away you go. Now, could you get away with any other type of a technique for getting it, not using a hull? Again, not very accurately. It is iterative as you move towards it, but we also don't want to take a ridiculous amount of time. Now, depending on these, if you think for a sec, do I really need a most likely path? We'll talk about how we can get it. I do want you to think a little bit about this, because there are ways you could fit some type of a spline to get close. Provably, it won't do the same thing, but the question is, when does it actually become close enough is good enough? Now, these are fairly large angle deviations. We usually don't like to use ones with that big of an angle deviation, right? So it becomes a little bit smaller. The big difference happens actually more within when there's changes in material density inside as you're moving through bone and soft tissue. The spline implicitly, or other types of, kind of smooth continuous action, is going to assume it's water all the way. Even with MLP, we start with that idea, though. In theory, you can correct over time and replace other materials, densities in it, but there is a little bit that accounts for there. The one advantage I would say you would get no matter what with an MLP is we not only get a path, we don't have to actually calculate it, but in the formalism, you also get the error estimates. So it kind of forms these banana-shaped curves, and you can find out where the most likely areas for it to go to as well. and that can be quite helpful. As you move to heavier ions, it becomes less important to do an MLP because the heavier ions deviate less and they'll get closer and closer to a spline-like path. So just side comment, right? Okay, let's talk a little bit about the paths and the problem size and things like that. We're dealing with a 3D area. So let's assume for a sec that we've got, somewhere around 10 million voxels. Now, I pull out that number of 10 million voxels because that's approximately how many, if you do 1 millimeter square or cubes, and you were to put a region around a human head, you're going to get about 10 million cubes, give you a little bit of boundary zone around the human head and fill it up. So that's the reason why I picked that 10 million as my approximate number there. Basic rule, and we'll show why later. You want about 100 protons per voxel is the basic kind of guideline to get a good image. Now, think about that. Normally, you can't solve it with less than a 1-to-1. So mathematically, you need at least 10 to the 7th. The interesting thing is to get a good quality image, we don't just want to solve it, we want to oversample it. Now, part of that reason is you've got to throw some of them out, some of it you do statistically to get rid of, but some of it, at least up to, until you get about 50 protons per voxel that you actually use in the final analysis, if you don't have at least that many, noise, which is always present in fairly decent quantities in most of these type of imaging techniques, particularly when we're doing individual tracking, and there are errors in path and all kinds of other stuff that we can be subject to. We're going to calculate a most likely path, but it's not the actual path involved. It's just the most likely one. So you need a little bit of statistics come into your aid on this. It'll be fairly noisy and not that beautiful until you get to that 100 area. Now, I made the comment about 400 voxels per path. If you think about it and you just go kind of across the image, right, that's where you get. But if you, take that basic, 10 to the 7th, split them up, right, put a 250, 250, 250 as the approximate zone around there. If you do 250 squared plus 250 squared plus 250 squared, square root of the whole thing, that gives you a diagonal through there, and that's kind of your worst case scenario. Your best case will be 250, right, when you're going straight through. So the 400 gives me kind of a more worst case type scenario to figure out, what could this be? Right? Square root of 3 times 250. So if your square root of 3 is about 1.7, so about an extra 70% added on. Anyway, so that's why I say about 400. That's going to become really important in a few sections because we're not going to do the standard data representation. And you have to understand that's really sparse. Imagine I'm really just hitting one voxel at a time. This isn't even 1 out of 250 on each side. And you can already tell that's a lot of extra zeros you're wasting time on. But if I just use those numbers, though, and I did a dense, like your standard linear algebra calculation, because this problem is just AX equals B, we mentioned. That's a known problem to solve, right? We've got linear algebra theory that has talked about this going back to Gauss, right? So we had an awful lot, even before there was linear algebra, we had the solution to this linear algebra problem. So we know exactly how to solve this. There's a whole bunch of ways, Gaussian elimination, QR factorization. Probably the most stable of those is SVD. So that's my comment about. The first one then is just the size of the A matrix. Remember, we kind of vectorize it. So, to take that one, you say, well, there's, 10 to the 7 voxels, right? That gives me the number of columns because there's 1 column per voxel. And then each row, that's going to give you basically 1 per proton path, because remember each one's a path. So when we kind of drew how that went up, the size of the A matrix that results from just linearizing this, 10 to the 7th column, 10 to the 9th rows, that means this takes a mere 10 petabytes just to hold the A matrix? How many of you have a machine with 10 petabytes of RAM sitting around? You don't even have 10 petabytes of hard disk space. That's about the hard disk space of our whole cluster, right? That's a pretty sizable research cluster's disk space. And that doesn't even hold B, that just holds A. So I want you to just realize the ridiculously huge size if we don't do something about this, right? And that's not just for this. This is any problem that tries to solve this. Ours is a little more detailed. So if you ever wondered, like, why they work so hard, if you've ever seen x-rays and that, and we'll talk about this when we talk about how to do filter back projection. We're going to work very hard never to hold all the data at once. We only load the B matrix, the sinogram, and then we're going to, when we actually do stuff, we're going to handle it basically one row at a time and calculate them as we need to. Because if you're to hold the whole thing, you got the same problem. This is not to hold the whole thing, this isn't just a proton computer tomography problem, this is a medical imaging problem, right? There's just too much volume. Now imagine going to a human chest, it's bigger than that, right? But anyway, we're already at ridiculous levels. How much, so space-wise, we're in trouble. How about time-wise? How much computation? I mentioned the SVD here because the SVD, you should learn a couple of the techniques that are out there. SVD is the most stable solution. Now, I'll be honest, it is also time-wise the slowest, but that doesn't affect this calculation, right? So all of the solution techniques for solving AX equal B are basically what are called n-cubed algorithms, cubed algorithms essentially. It's an n-cubed algorithm just to multiply matrices. So, essentially you're not getting away from this, right? The coefficients, so you get basically n cubed and then, there's a coefficient in front. The coefficient in front of this one is usually up to about 6, like the number 6, like literally it's. So it's not a huge thing above this, but other ones might be down like 2. So we're not, when you're talking n getting large, the fastness or slowness of one versus another is not very significant. They're all within, 3 times, maybe 4 times each other, speed-wise. What would this take? Well, what it takes for SVD, and I picked this one, number 1, it's the most stable, so the least likely to get error. Number 2, since it's the slowest, but still on order, it's at least a fair representation to give you an idea of about what time periods you're taking. So it uses the column times the columns times the number of rows. That's a pretty typical setup. When we said cubed, right, it's 3 of the dimensions, but it's not a square matrix, so it's not just literally n cubed. You have to. We usually call the rows m and the columns n, so it's n squared times m. Okay, and that's for the more economic one. If you use the less economic one, you can actually get up to rows in, or sorry, the m cubed number. But anyway, if I do the efficient one, that's still 10 to the 11th teraflops of operations, right? I mean, now think about that one for a sec, right? For a teraflop, so that's maybe like 1 second's worth of thing. If you were to turn that on a modern machine, you're talking like 1,000 years. You could parallelize across a cluster and things like that, but if you took a desktop machine and tried to solve this, number 1, it wouldn't fit, and number 2, the most direct way to solve it, there'll be a whole new political map by the time the answer is done. So it's, think about what the political map looked like 1,000 years ago. So, Vikings were still reigning and stuff like that. The Crusades were going on. It's a big period of time. So my net result is even if you speed it up on a cluster and I get it into a reasonable framework, When I started looking at this problem, it took several weeks to get an image with parallelization. So it still would, and that's doing some of the more efficient methods and things like that, which doesn't actually calculate this complexity level. But just realize it's not possible. Those direct, obvious techniques, they're lovely and can work for small problems. They are the right thing for small problems. Intuitively, you'll learn all the important stuff for the small problems, but it's not the way to go. Fine. Okay. How are we doing so far? Fine. I know there's temptations for other stuff, but I guarantee you, I'm giving you a lot of little hints in here that's going to relate to other stuff. So now we want to take a look at things we can do to try to simplify this. This one is going to be actually an advantage that's going to save you both some time and memory. Now, what we did for this one was we took a look at how many histories had a particular, so we have this idea of a bin number, right? So we took a look at how many exactly voxels they went through, what the path was, right? And there's a lot of very similar paths that ones have to take. So the question was, could I actually take advantage of trying to do things in some kind of characteristic over a group? Could I bin them together and deal with similar ones at the same time that are going through similar voxels, so I don't have to keep reloading memory, right? So if I get ones that happen to deal with particular voxels over and over again, right, I can just load that particular bit of memory up, do all my calculations in that space, finish it up, shove that out, pull in the next chunk, and I can rotate through. And if you notice on the side, fairly typical for these, we're getting at least for most of them, decent number of them. Yeah, minimum's 1,000, but honestly, the low end over on this side is almost up about 4,000. So, and I can get up to, the high point, the most commonly hit ones, I'm up to 16. That's a fairly decent number of ones mixed together. So it does suggest that I can kind of batch things spatially to be able to take advantage of memory loads to be more efficient. And indeed, that is one of the things we're going to do, is we can batch load these and calculate them in groups, and it will save us a lot of trouble. The second thing we want to take a look at is how to represent this path. So, here's a path going through, right? You can see, imagine I just had everything, 0 means I don't hit it, 1 means I hit it. Right here, I just numbered them. If it got anywhere close to it, I called it good. So I marked all the ones on them. If I were to then vectorize this, and this is just the layer it went through, if I were to do that whole thing, I'm storing way more zeros than ones. And that means I'm calculating a whole bunch of 0 times something. Well, anybody know what the answer to 0 times something is? 0. Why calculate it then? Right? I mean, why do the multiplication for, there's 400 of these dumb things out of, 10 million columns, right? Only 400 of them hit. So, 10 million minus 400, 0 times something. I am spending 99% of my time literally calculating nothing. I mean, and as true as the sense of calculating nothingness is out there. So what can I do to avoid having to do this? And I have to store all those zeros. Why store them? They're nothing, like literally. So this is what's called sparse matrices. This comes to the rescue here. Everybody ever hear of sparse matrices before? Right? So what do you think sparse matrices are for? So think about what that is. Think how many things are sparse in the world. Right? So imagine that I wanted to talk about just how space-time is working together. And I'm dealing with, gravity of planets and everything else, right? Do I pull on Alpha Centauri, the closest star after our own sun? Yeah, of course, right? Now, if I had to look at that when I'm calculating, like the distance between me and it, I could also just aggregate it together locally, right? And that would save me an awful lot in calculating stellar geometries. How about when you calculate, let's say, a problem, you're solving a circuit problem, and you're going to do Kirchhoff's laws, right? So I don't care doing node or loop, whatever floats your boat for that, right? When you calculate those, does every element in some way in a circuit affect every other element? They all appear in the equations. I have a large circuit, lots of nodes, lots of elements going off, different loops. They're not going to appear in it, right? So, in essence, for a lot of it, I don't have any cross connection. The connection is through other elements, It's a trickle down, right? You can do superposition, all kinds of other stuff. But that means most of the interconnections between the elements are zero. So if you write a matrix for this to solve the equation, it's mostly zero. Mechanically speaking, right? You could have a bridge truss problem. You see all these kind of girders between them, right? Forces have to basically go down those girders, don't they? You know, or you see a suspension bridge and it goes down the cables. It doesn't go between the other parts of space. So most of space that you're solving the problem in is nothing. And nothing's moving between two unconnected cables. It's a sparse matrix. I'm just trying to encourage you to understand that in reality, this is not just a rare thing happening here. It turns out pretty much all of engineering does sparse matrices, from astrophysics down to standard stuff you want, and if you get down to the microzone, it applies there too. So they're almost all sparse. It is really the general way. So this is a very useful technique to be aware of for how do you store things. Because it not only saves memory, it saves time. And that's probably, they're both arguably important. Let me just take a quick example, right? What I want to do, you can see here a sparse matrix. A sparse matrix is basically a matrix where there are much more zeros than there are non-zeros. I'm just going to split them into those two groups. Now, to store a matrix, I can either store all the elements, or I can just store where they're located. If I said, you know, in the 1,1 element, I have a 3, right? And then in the 1,4, I have a 2, right? So on and so forth. You could recreate them, right? And it would take 3 pieces of information to hold it the alternate way, right? Store the row number, store the column number, store the value. So I have to store 3 pieces of information. But if you're mostly zeros and I can chuck them away, i.e. you've got, you know, at least 2/3 of your matrix is 0, and the rest is non-zero, it actually takes less to store all the info for it. In our case, we're way beyond that. In most cases, A and decent size problem, you're way beyond that. Right? Now, besides that one, I don't even have to store all of it. So that's what some of these ones are kind of going in. So the first off is we get the non-zero array. If you notice here, that's actually just the values, right? The 3, 2, go to the next row, 6, next row, 1, 4, next row, 5, 5, next row, 3, right? Next row, 9, 7, 6, last row, 1. So that's just the non-zero elements walking row-wise, recorded down. Those are the numbers I want. Now, I can have a column index, right? This tells you, right? That 3, we're going to start numbering from 0. So column 0 is where the 3 is located. Column 3 is where the 2 is, right? So on and so forth. So this has which column can you find it in inside the matrix. Now, I could have a row index matrix here. But rather than do that, what we do is every one of these is going to tell you a different row. So count your rows. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And that one tells me I'm all done. So the first one, 0, points here. This is where your first row starts. Your second row starts at 2. 0, 1, 2. So it points here. Right? So now you know this is where 2 is, so both of those are obviously 1. I don't have to store that both of these are 1. Once I said this is 1, until I tell you it's 2, you're in 1. So I don't need to store every single row indicator, I just need to have a pointer. And then I want one pointer to the end because it's just helpful. It takes one extra entry, but now you have a marker for the end of your array is, because sometimes you want to start at the one end, sometimes you want to start at the other. So it just makes it cleaner to just be able to have pointers on both sides. So you need rows plus 1 to have both the start and the end pointed at also.
So it's kind of the equivalent of storing how many are in each row.
Essentially, right? You'd have to calculate that number off it, you know, and this one just tells me when it ends. I mean, you have to know at some point when does it end.
Right.
So you're either going to have to put some type of a terminator or an absolute count or whatever else.
Right.
If I put it here, I've got an absolute count on the, you know, so it avoids that problem. So, but it also works as a pointer to tell you where, if you want to add something to the next one, it tells you where to start the next pointer on it. So it just, there's always nice to have that extra piece of information. Good? That makes sense how that works?
I didn't get that last row, or that last row pointer.
Okay, so this says, this is the start of row 1, number 0, right? So it says, you know, go to element 0 here, the 0 element in this. This is where your first row starts. 2, 0, 1, 2. That's where the second row starts. Right? So they just kind of point and tell you who's what. I think I actually put some arrows on the next slide. Let me just check. Okay, well that gives you an example. Let me. I'll just use it as it, right? So if you look here, right, the 0 points here. Let me see if I can slide this up and I can draw on the back.
Third row at the bottom, all those numbers are the indices of the array with numbers. So 0, first element.
Yeah, it's literally a pointer's index of where the element is on the next one.
So it says
So,
0th element of your
This is element 0, right? So if this was column index, right? So this is CI. This element right here is CI element 0. This is CI element 1. CI element 2.
Yeah.
Make sense? Right? CI element 3. Okay. So this 0 says the first, right? This is my first row. And it says it starts at element 0 in the column index. And the second row starts at 2, right? So I have to go and point to one in element location 2. So implicitly, since the first row started here and the second one goes here, this has to be part of the first row. Has to. It's before the second row. So, I mean, technically speaking, you don't actually have to, the first one should always be, in some sense, 0. You know, unless there's no first row at all, I guess you have a -1 saying there wasn't a first row. But implicitly, it's an assumable information. That's kind of what I'm saying with the ends, right? Technically speaking, you could infer those, but then when you're writing code, it's not very clean. You have to write an exception case for the ends, right? And it's often better to just put in the extra little piece of data so you don't have to write exception codes.
Yeah, it's just one.
Yeah, it's not like you're even talking and, it's literally 1. You're going to spend more memory writing code to handle the lack of a value. So it's really, in my opinion, it's foolishly wasteful. You know, it's where you get so efficient you're bad. So this just gives an example, right? If I take a look, this is the third row. of the matrix. You can see that one that's up there, boxed in, right? So the third row, right, up. So actually I should, yeah, third row, and this is looking to position or index 3, CI3. That's my third row. And it says it's in the column, right, is number 2. Now that doesn't actually say to go here. You just stay within the same vertical column to get it, right? Because these are exactly lined up. So this just says, right, that my index as far as my row is 0, 1, 2, right? So, right, I'm now at my third row. That's index 2, right? This is on my third column, index 2. So that tells me the 3 element of that array is a 1. Right? So this one is a pointer, and you infer its value by its location in the list. This one actually tells you the value of the index in the list. And that one tells me what's stored at that location. Right? So offset 0, 1, 2, third column, at 2, that's third row. At location 2 in the column index says third column, so 3 column is a 1. Does that make sense? I think I've got a second example here. Okay, so, notice the next one down, right? So this is first row, I already wrote that, first row, second row, third row, fourth row, which means when we're numbering the fourth row, that would be a 3, right? But because we're just numbering rows 0, 1, 2, 3, that's here. Right? So I go to the fourth row, index 3. It gives me the number 5. That tells me the index to go to here. 0, 1, 2, 3, 4, 5. That's why the arrow points. Right? So this one tells me the column. Right? So I'm at row 3, and the column number is 2, right? So that's the fourth row in the third column. And that, in my original, let's say that matrix was A, it's saying A32 is equal to, and you just keep the same exact 5 index for the value array, because the column index and the value array are always coupled. Right? Because this is the only one we compressed. That value is 5. Right? So A32 in the matrix is 5. So we try over here. A3, 0, 1, 2, 3, this row. And then 0, 1, 2. Right? That's the third column. The value is 5. That's what that told us. Right? Fourth row. Right? This is third column is a 5. Okay? And then the next one wouldn't go till 7, which is over here, which means this one is also part of the fourth row. Also with a value 5, and it's just one column over. Good? Makes sense to read them? So notice this is significantly smaller because I'd only be storing on average 400 of these. And, 400 of these. And depending on how many rows, what the angle deflection is on this thing, it will never be more than 400, but it's probably going to be more in the order of like 10 or 20. So that's a drastic reduction from 10 million. You know, we're talking from 10 million to less than 1,000. That's a lot of space saving. Okay. Anyway, so that 5 tells you where the next one is. That says both of those ones with 3 arrows on the next slide are in the same row. Yay. And indeed, 1 and 4 are both in the same row. Good? Yay. Fine. So again, points to this, this points to the next, anything up to that is in the same row. Okay. If we store sparse, it goes down from umpteen petabytes to, if I stored it, down to a terabyte. This is more in reasonable range, right? So, yeah, I mean, this is in RAM range even. So it goes from, you can't store it on a cluster unless it's a big cluster, to you can store it on a laptop in memory. Anyway, so that's a fairly good improvement on your spatial area. We feel good with this? Okay. The other things that we can get is if we switch to POCs, right? Everybody familiar with POCs? Projection on convex sets. We'll explain the idea in a second if you don't. The particular version that medical people always love is called ART and its derivatives, algebraic reconstruction technique. But it's basically a POCs algorithm. And in this particular case, you know, it becomes drastically reduced. This is how many items are inside that storage area, right? So now we're down to, with sparse structure. Since we cut it to 10 to the third as a size to hold stuff in, we only calculate the non-zero values. We're not going to calculate the zeros. So it not only cut me down to 8,900 for a typical area for storage, it also cut me down to 8,900 is what I'm multiplying, and I've got 10 to the 9th of them. You know, I still have a number of rows, but that's actually extremely manageable now. Okay. We don't need to see all that. So let's actually talk about how we'll do these type of calculations. Just out of curiosity, how many people have seen POCs or some other type of similar type of calculation before? Okay, one person. So we're going to deal with the two main things that we have to do. One of which has to do with the most likely path. How do we actually calculate it? The next part we'll deal with will be actually what does POCs or ART and its variants look like. Okay, so let's assume this is the object boundary, these lines here. I haven't drawn the whole thing because I'm just truncating it. So this is air. We've got protons coming in from this direction. I drew a bunch of arrows because initially I drew one and it was right on the line. It was really hard to see. So I added a few more friends just so you kind of, they're more obvious where they come in. But we're really calculating this one in the center. It comes in, it hits, and it kind of bounces around to different spots, right? This is kind of the actual spot that it hit. We're assuming that is this kind of red line that it went between somewhere, or there was some amount of interaction that deflected. The higher the energy, the more spread those ones are. And it goes around until it eventually comes out at some angle and then, you know, eventually hits the registration plane, right? So this is the entry plane, the innermost one, that's the innermost one at the exit. And so this is the projection to the boundary of the object, right? That's the actual thing I'm claiming. But what we're going to want to do is calculate this blue line, right? The most likely path. So the first thing you should realize is it's not the truth. There is no way you can know the truth, right? This is in the realm of God, okay? It's just, you don't know it, you know. So the best you can possibly do is to be able to get something, you know. Now you have to argue what does even best mean. But we're going to say best is given the information available at hand, what would be the highest probability? What's the most likely path that it falls on? And that's what we're gonna take a look at. Is probabilistically, given the motion of a proton, where would you say it would go? The higher the energy of the proton, the more it will conform to that path. All right. So, what we have to do is write a likelihood. This is kind of Bayes. We're going to assume that the spread and the bouncing around and stuff, Coulomb scattering, is essentially going to be a Gaussian distribution process. Right? So I have written the Gaussian likelihood. 0 is the entry point where it touched the object. So that's the boundary at the entrance. Y2 is going to be the same exact point on the exit. So the edge of the material. So if it enters here in my head and then exits here in my head, the entry is Y0, the other is Y2. Y1 is any point along the most likely path we want to calculate at this moment. So we didn't want to, we argued, should we make it N, but then the question was, what do we pick as the in-between one? We didn't want to kind of pick them, so we just said, hey, look, entry, exit, you know, the 0, 2, and 1 will just be whatever you want. So what is the likelihood that you're at some middle point Y1 along the path, given that the entry point was Y0? That's what we're writing. And that has to do with how likely is it to bounce and spread around. Okay, well, what is that based on? Well, Gaussian probability, so it's going to be proportional to the e to the -1/2. And then everybody remembers what Gaussian looks like in just one dimension? What does it look like?
You mean the equation?
What's the equation? Yeah.
Well, it's negative u minus the center squared over.
Okay. So goes right, it's x minus the mu, the mean, right? Quantity squared over
Standard deviation.
Standard deviation squared,
Right.
right? And so it's -1/2. So if you look at this, -1/2, then we've got a term, this is for matrices. So I've got a linear term times the same exact one, the transpose. That's your square term on top. And then you have this basically spreading or standard deviation of how likely things are going to change matrix, which if you look at it, it's all squares of standard deviations. So the basic form of this, just written into vector, is e to the -1/2, thing on top squared over thing on bottom squared. And thing on bottom squared is a standard deviation. And the thing on top has to do with y1, where you're at, that's the x, minus kind of where you would expect, given the entry point, where's the likely spot it would be, i.e. the mean projected out. So this is kind of working like an x minus mean, squared, either side, and then the sigma 1, that's my bad, that should be with a -1 power on top.
Okay.
The sigma should have a -1 there. I just know, sorry, I'm writing this, taking it from our actual thing and writing it into Microsoft's equation editor, which I totally despise. So yeah, there should be a -1 at sigma 1 to the -1 power.
Is the transpose matrix supposed to go first?
Yes.
Okay.
Because as a convention, this is a numerics convention, so in numerics, particularly in engineering, we make the assumption that all vectors are basically a column vector. Right? Now, you don't have to, and in math, they don't make this assumption. In physics, to avoid having to make that assumption, they make two different things, bra and kit, when you go into quantum. Right? If you've ever do quantum. No. Okay, then that doesn't make sense. But they try to avoid this thing, which one's a row, which one's a column, and they just name them two completely different things. And they use a different symbol. You've probably actually seen the notation for them. If anybody's ever seen something that looks like this, in quantum, You ever see that type of stuff going on before? All of this says is row vector of A, column vector of A, because it was way too difficult to write that. That's all they're saying. But dang, doesn't that look confusing as heck, right? That one's called bra, and that's called ket because it makes a bracket, a bracket. Yeah. Thank you, quantum physicists, for making something that was simple into something almost unreadable. Sorry, yeah. But that's life. Anyway, so this problem of which one to assume is on there. When you're trying to calculate to a single scalar value, which I kind of need to in this case, you need a row times a column gives you a single value. So a row, right, this transpose makes a row vector out of this, times a matrix, which I forgot the inverse on, put the inverse in, right? That will give you that times this is again still, right, row times matrix gives you row. And then row times column gives you single value entry.
Is the sigma 1 matrix determined before we do this?
Yes, so again, remember how I mentioned that we can kind of group them together, that's properties of the material?
Mm-hmm.
We can group those properties by how deep it is.
Okay.
And one of those properties restores that sigma matrix.
Okay.
It depends on the material. So, you know, each one of these, it's fairly straightforward. You know, this is the standard, well, let me start down here because I think this is most likely to understand, right? If you just did sigma theta 1, what that's saying is, what's the likelihood, spread-wise, the standard deviation, in angle spread of a beam coming in, right? For whatever material is at that depth. So sigma theta tells you that's here, the sub 1 tells you it's the property of that center. In general, when we first start out, we assume it's all water, so they all have the same theta, so I could just put sigma theta quantity squared. But later on, you might actually want to get different materials accounted in for and kind of use regional materials. So leaving it in just lets you realize where it goes. This one is, what is the likelihood slowdown, the attenuation, right, that goes on with a lateral dispersal. So it slows down and you get lateral dispersal. So this is angular, and that's the spatial dispersal that goes on. Okay. Right? How likely is it to have, by this point within it, encountered from this slowdown this much of a deviation to the side? And this is how likely is it to be bent at an angle when we're going in? And this is the cross correlation. Okay. You know, if I'm off some distance t, right? So u is in, t is the offside. So as I'm getting slowed down by these things, I get spread and I get offset. Well, if I've been offset a certain distance and I'm at a particular angle, how likely was that combo? That's what the cross covariance is dealing with. That's essentially the meaning of them. To calculate them, you have to do an integral of the path up to that point, right? You just kind of add up what was everything up to there. But it's not that surprising. It looks scary as heck when you see it in integral form. So if you read the paper, so this was all stuff, this was actually part of my contribution to this, was what this equation looks like. But anyway, the calculation is kind of ugly to get those coefficients, but it's not a surprising calculation, right? Add up all the coefficients and boom, there you go. This one's kind of a fun one, because everybody always gets flipped out because it's essentially non-symmetric. But this is, you gotta think what R is saying, right? So you start out at 0, 0. Right? And when you're listing these points that's going through, Y1 is not just a single point, even though we're just considering the plane, it's a point and an angle. So how far off is it in one direction and what's its angle? That's Y. So it's the position, the offset position and the angle. We're not considering out of the board because it's the same exact equation, so you just do the same thing out of the board, but it's the same equation, so why calculate it twice? Right? So we just essentially just do the smaller equation and then you get the one out of the board It's the same exact equation. So this is saying basically the spread, if I started with an offset, how likely do I still have that offset? Well, that should be linearly proportional, right? If I started dead on center, you would expect on average it's probably going to be dead on center. If I started, you know, a centimeter up, I'm more likely to be a centimeter up than not, because I'm coming pretty straight in, right? And this one is saying angle-wise, if I came in at a particular angle, that's kind of my median angle for things to be at, right? Deviations would have to switch it, but they're gonna go. Now imagine if for this one to be, this is how far you've traveled through the material. U1 is my depth in the material now, that's at the entry point. In general, this is 0. So I really could just write U1 there. But I always like to write U0 just because in practical reality, your entry point is not the 0 point because your object is partly through the grid. So this just says, how much stuff have you gone through? Well, if you started an angle and you're going through stuff and the angle bends a little, that angle bend, right, the amount of angle on it times the distance gives you the displacement. Do we agree? So if I started, imagine it didn't do any interaction at all. And let's say, here's me entering the material, and here's the depth of plane that's in. If I start at 0 with angle 0, right, then I'm gonna base assume it doesn't shift up or down any. And we're gonna assume that it also doesn't deflect any, so it's gonna project here. Right? So let me just call this 0 for simplicity and this U1. Then you would assume this point over here, right? If I entered at 0, 0, you would expect that I go to 0, 0 on this one, right? Angle 0 and position 0. If I started at 1, 0, you'd expect it's going to go straight through and hit 1, 0. The first one does not change just because you're offset. It makes no sense that it would change the angle. Do we agree with all that? Okay. What happens if I come in at 0 at an angle? Well, you would expect it's going to continue on path, as that's the base assumption. We're just kind of projecting it down the line. So if I started at position 0 and some angle theta, right, our angles are really small, right? So if this is theta, what's this component here? Right? So you have to take whatever your, what was the path length you took, right? And this would be sine theta times whatever that was. Now, if this angle is really small, what's the difference between this side and this side? Right? So if I took, if I had a really small angle, what's the difference between the length of those two sides? Pretty much not, right? Do we agree? And you can think about this, the small angle approximation for cosine of theta is 1. It's just 1. It's flat. Okay? So we assume those two sides are the same. So this is actually the U1, the depth in the material. But since it's a small angle approximation we're assuming, we can assume the travel path down that distance is U1. Small angle approximation. That makes this U1 here. That's why it's U1 minus U0, because that's really, that's U0. I just dropped the other one for simplicity. So that's where the U1 minus U0 comes from up there. Right? Small angle approximation for sine of theta. Theta. So this, when you get to small angles, right, becomes, this is U1 minus U0. So this becomes U1 minus U0. It's a small approximation of the length times the small approximation of the angle. That's just multiplied by theta, assuming you're radians. Agree? Well, remember our positions. This is your displacement, and this is your angle.
I think it's more intuitive when you understand the y is position and angle.
Yeah. Right? Once you see it, everybody goes, oh yeah, of course. Right? But, yeah, like I said, you just kind of have to see it when it goes in. Okay. You do this equation. Do we agree then? Right? So this is kind of, you can think of R0 times Y0 is the mean, the most expected path, nothing happening. Most likely thing, it just keeps right on going, you know, without considering anything else. Right? That would be my middle. It just keeps on doing what it's doing. Right? So that's kind of serving like my mu. That's, you know, my x minus mu, pi squared over sigma squared, boom, away we go. Does the equation make sense now? Why it is what it is? Yeah.
So is this recursive per depth?
So the neat thing is we didn't say what it was, right? We keep all of our angles. The entry and exit one, it should make more sense that I ideally want these to be a degree or less.
Right.
Right? Because then small angle approximation works.
Right.
You know, it also means that we didn't hit any of these weird bend things. So at the energy levels we're at, it's true, provided you didn't have a nuclear interaction, which is always throws things up for grabs. All right, the same equation holds true just backwards from the other end. Do we agree with that? So this is why it's kind of like a banana-shaped curve. At the end points, there's like no uncertainty and they spread towards each other. Okay. So I take both of those. So given my entry and my exit, right, I can write the likelihood ratio. I take both of those, the likelihood that both are true, I multiply them. So that's how you combine your probabilities, right? So that gives me my product, and I minimize that, which means take the derivative, set equal to 0, and solve for what's the value of y1 that's true on, and that'll be the y at that particular offset. That is the point along the curve. Make sense? It's straightforward. It's a matrix equation, but you know, in an exponential, but it's not that hard. So we can write this as this. Here I remember the minuses. So you can see them with the minuses in. You know, the R0 is from the direction of the entry. The R1 is from the direction of the exit. And I just multiply through instead of having the two separate ones with a minus, and I did the transpose and multiplied them because they stuck together. And then solved, because you have to separate the y's out from it. All right. So if you think about it, right, we've got the sigma 1 inverse. The sigma 2 inverse is from the exit direction, because I might have gone through different materials along the line. So that's at entry depth what it was. So that's why I was talking about how much depth it went through in bidding them. So we, you know, 90% of the ones use like 20 or 30 different values. And there's really only 3 entries in those because it's symmetric for the sigmas. So, you know, I got like 200 values to store, you know, for depth for both directions, one for the front, one for the back. You know, and away we go. So, I mean, in this sense, it's, you know, I've got like maybe 1,000 values to store and hold all those matrices. Right. It's a fairly straightforward calculation because you're not actually going to calculate the sigma 2 inverse. You're going to pre-calculate it and store the value of the pre-calculation. On top of it, most of the time we only care about the displacement. We don't care what the angle is. So we're only going to calculate the top row. We won't calculate the second row. So if you only do the top row, you group up the 1,600 possibilities from that curve I showed you that was on, you know, for this, you know, 1,600 possibilities for 10 million. It's, again, a pretty good return on investment. I can take this down and calculate the whole thing in 79 floating point operations for a whole step. That's a pretty nice little maneuver to get it. And this is what it kind of looks like. You know, these are just the stored value variable names, and that's the entry in the matrix that it's wanting to calculate. So we have these kind of pre-calculated pre-4 and 5, which calculates those particular entries in here. And then we can multiply these by the particular entries in the vector. Right? This is the exit one, that's the entry one. You know, calculate those ones there. So this is what was the effect from entry, the effect from exit, and you can find out your MLP from that rather simple little calculation. You know, so from the 79 operations for doing that one for 2x2s, you're actually down to now 1, 2, 3, 4 multiplies and 4 memory lookups, 3 additions. Not too shabby. So I submit to you a much better calculation. So very, very fast. So that's how we do our most likely path. Therefore, it doesn't make any sense to store this because it's just too stupid easy to actually, it's smaller and it's faster to calculate this way. So this is Catchmark, one of the first inventors. So when we were talking about POX, so I mentioned we do history. He's kind of an interesting guy. See his death? Right? And if you look at his name and take a look at his death date, you should be able to figure out what happened here. Right? It might not be as obvious at first. You have to know at Catchmark where that name comes from. Polish. It's a Polish mathematician. Now look when he died. So who is that? That'd be the Nazis. So he was a part of the Polish resistance against the Nazis, and he died fighting them in 39 when they invaded Poland. So, you know, he wasn't a particularly old guy. I mean, he's, you know, bald and all, but, you know, but that didn't really mean an awful lot. Anyway, so it's just kind of one of those like tragic little understories of history. You know, what else could he have done if he came up? This is really before computers. He came up with one of the fastest methods to calculate things on a computer. You know, that's like, you can only imagine what you would have been able to get out of the minds like that had they been able to live and there wasn't stupid people like Hitler around. Anyway, so this is the ART method is also, it was rediscovered and called ART. So some people call this Catchmark's method in honor. It's very implementable as sparse. It's, you know, a nice parallel algorithm. There's versions of them, right? So there's fully simultaneous, we call it Gemino, you know, or component averaging. That's another one that's a fully simultaneous. There are ones that are block iterative algorithms. You group up the rows, the histories into blocks, and you calculate them. We'll talk about what each one does. Another one where you group them up into strings of operation, and you have independent strings that allows you to parallelize as well. So those are the parallel versions of this algorithm. It turns out for GPUs, block iteratives are really good. If you're dealing with large traditional structures, you know, like you got a big cluster of a whole bunch of parallel machines, like I take all the machines out here and turn it into a cluster, it's usually going to do a better job with string averaged. So the hardware design, how they're physically built, so if you've ever taken comp org and things like that, and you wonder, why does that really matter to programming? It turns out the effect of those, how memory is accessed, how they interchange between each other, is going to force on traditional machines that have a string average. On lightweight GPU calculations, it's going to favor the block iterative. Anyway, so let's talk. I'm going to do graphically what ART is. Okay? So right here, imagine I've got some solution space. You can kind of see a faint circle. All right? This is my initial guess. So imagine I've just got a two-dimensional thing. X is a two-dimensional component. There is you know, in X, like the first component and the second component. And I'm going to take some guess at what that is. Okay? And that's what you see here. All right, so I'm guessing this. So I'm guessing a tiny amount in the first component and a much bigger amount in the second. But that's my guess of what it is. So maybe it's like, you know, 0.5 and 7, right, for my you know, vector that I'm assuming here. Each of these green lines is a row, right? This comes from a linear equation, AX equals B. So AX equals B, each row forms a line implicitly through space. The B is an offset in essence, and the AX kind of gives you the slope. So each of these is going to determine a sloped line, some offset. And what you're trying to do, all of those lines, if it's a consistent equation, they meet somewhere. If it's not a consistent equation, they don't meet somewhere. But we're trying to solve a consistent equation. So we want to find out where do they all meet, i.e. where each one of the rows can be satisfied. If all the rows can be satisfied, there's nothing left over, therefore it solves it. So this is our problem, AX equals B, right? A and B determine these green lines. I take a wild guess. I'd like to go from wild guess to actual solution. Make sense? Now, one way I could do it is stick it in the dense formula solver and just get the answer. Right? For a 2x2, it would be fast. But let's see what we can do here. Imagine I took just one of these rows and I projected onto it. So I forced it, by projecting it, I'm forcing that equation to work. So I'm making it, I'm solving one equation, say, find me the closest spot in that equation space where this works. That's exactly what a projection does. So this is an orthogonal projection onto one of the rows, the row space. Does that make sense? Okay. So I can find that. I'm going to call that my new x1. I'm going to take this and I'm going to repeat. I pick another one. I orthogonally project onto it. Right? That's going to give me my new guess, x2. Now, what do you notice about x0, x1, x2? It's getting closer to that center, isn't it? So you can imagine, as I pick another one, it projects. Pick another one, it's getting closer and closer and closer. Right? Now, I've picked these so that I go through each one of them without repeating. So I only let you use it once. That's not a hard requirement, but it's a pretty important one. And you walk through all of them. This is one complete cycle. I can then start over again because I've got a new one. But after one cycle, I want you to just notice it's a lot closer, isn't it? Good? Okay. That's art. That's really what it is, right? The equations will vary. You know, actually, let me do one other thing before we go on here. This. Imagine, so this is one of those kind of neat points we take. Imagine, let me raise this up so I can draw on this. So we said we're going to project onto things and take, and we're going to take the kind of net result of this, right? The new projection on. That one goes off my whiteboard. So I'm going to go from x1 to x2. What if I did the projection, but I only went halfway? Does that make sense? So imagine, so I'm just going to start here. Roughly imagine that's halfway. What if I took that to be my new x2? Right? And then x2 I project down to here. And then I go halfway. All right, and then here, and I go halfway. You notice something interesting kind of going on?
The convergence is more stable than solid.
Not only is it more stable. I'd actually even argue if you just took a little tiny bit in, you know, took 90% or something. Right? It's kind of more stable, but it's on the inside track, so to speak. Right? Whatever you do, I'm closer. It can be a lot closer, it can be a little closer, but it's kind of always got the inside track. So we're going to call how far you make that jump, we're going to call that the relaxation parameter. And here would be my intuition. Imagine you're chasing to this point, right? But it's moving all the time. Does it make sense if you're trying to catch something to follow every point it went to, or try to cut the corner and take the inside track to intercept it? Try to figure out where it's going and kind of predict ahead. It would make a lot more sense to do that one. So it turns out by taking a little bit less, not going the full way, you kind of go part way and go, oh, I should start correcting after it to pursue it. So it's a better pursuit algorithm not to go the whole distance. I just want you to have that intuition, right? If you understand that, it's going to turn out that's going to be a very helpful principle when we're doing the calculations.
Is there any drawbacks to over-relaxing?
I could choose it all the way to 1 if I want. We'll just get a thing, how far do you go? 0.9 will be 90%. For a typical algorithm we do right now, the actual value, like I hit on most of my matrix ones, is down to around 10 to the minus 4th. Right? Where 1 is using all of it, 0 is using none of it. It's really small. The number I pick will be proportional to how many histories there are. I've got a lot of histories, you know, so I get it down there. If you were looking at something that's around 100 items or something, you're probably somewhere around like, 10%, 100 to 1,000, something like that. If you're dealing with less than 100, you're probably at 0.3, 0.5. Anyway, let's just take a look real quick. Some other ways people have done the same idea. What Cimino, an Italian mathematician, did is he said, well, what if instead of kind of going one at a time, walking through all of them, what if I projected onto all of them? Same time, just initial estimate, I projected onto here, and I projected to there, and to there, and to there. Right? I projected each of the histories. If I take those points as kind of like the corner of a polytope, some oddball shape connecting all those points together, then the space between there is any possible weighted sum of them. Right? So I could pick any of them, but let's say I took the center of mass. Right? Notice what happens. That's a big improvement, isn't it? And think about, can I do this in parallel? I absolutely can do this in parallel. Right? Now, Cimino wasn't copying Cashmark. We can actually prove this because Cimino did this in 1918, the end of World War I. Cashmark was not aware of this because this was in Italian and Polish literature didn't blend super well. Different language and everything. Not everybody was aware of whatever's on. And this one was, to the Italians, the respected way to do it. This converges in general slower, but it's totally parallel. Each one of these can be done by a separate machine, and then you combine them together. So it's crazy good speed up on a cluster. That's my warning. I'll just go real quick through some of these because all the rest of these are similar ideas. Imagine a string average one, right? The idea is I take my initial estimate, I take 2 of these, project from the first to the second. That's my first string, 2 projections in a row. I pick another string, 2 in a row, but I have the other one in shadow in the background, right? I do it for another one. I think I've got 6 of these total. So now I've got 3 strings and their endpoints. Here, here, and here. right? From that same initial guess. I make a polytope of that. So it's kind of like partway between art and partway between Cimino, right? I've broken them up into art-like strings and I combine them like Cimino. Okay? And then I take the center of mass. Look how good a job that did. Right? Actually, the longer the strings, the closer it's going to get you. It's going to be more like art. Right? But the more strings, the more you parallelize it. So now you can trade off how much do you parallelize it by how fast does it advance. Right? That's a pretty helpful kind of trade-off to be able to understand easily. The block iterative ones, imagine each block does a Cimino. So ultimately I pick a group of, like in this case, 3 of them, and I do Cimino off of it. Right? And I use this as a new, that's my new guess, but it's not a completely finish to this whole thing. So I'm kind of going to do art on Cimino blocks. So here's my first block, and then I take that little X1 and I do my second block. Now I've gone through the whole thing, I finished one cycle. Right? GPUs really love that Cimino-like structure. And then doing them in sequence over it lets you get a kind of a nice convergence to them, so I can get groups at a time. And that allows me to make different GPUs, right? So that's why this is very efficient on a GPU. And you can kind of see, so that's really from the first to the second. I should have called this like 0.5 and called that 1, because that's that's the end of the cycle. But this one's the one that's going to turn out to be efficient for us. We don't have time to go into it now. I'll talk about the equation. I'm going to steal a little bit of time from next class. We'll start this off, and then we'll talk about how to do filtered back projection. This one will give you the insight into how do you actually calculate. That's the equation we do to update. X is my guess. That lambda you see in front, that's that relaxation parameter, how fast you make in the corner. You know, the WK is how do you choose the weighted center. You average them all, whatever. You know, you have options. And the rest of it's just the projection for the line. So, and then I've got the little graphic picture, but we'll walk through what each one means next time. It should only take us maybe 10, 15 minutes. All right, have a lovely weekend. If you have questions, I'm happy to answer.